So we are really happy to have Yacine. Yacine did his PhD from Orsay in France, and his initial work was on small x structure of the nuclei. So, I mean, if people know keywords like gluon saturation, etc. And he worked a lot on the initial state of heavy ion collisions before the formation of the QGP. And then he's been continuing some of that work in Heidelberg and Seclé and USC in Spain. And then he eventually became postdoc at INT, and now currently he's a faculty member at Brookhaven National Labs in New York. And after his initial work on the initial state of the QGP, he has also worked a lot on the properties of jets in heavy ion collisions and the use of and the extension of techniques like jet substructure or jet grooming, which are used for PP collisions to heavy ion collisions. So today he'll talk about wave turbulence in the QGP. So the floor is yours, Yacine.
Okay, thank you. Shall I start or?
Yeah, I think you can start. Thanks.
Okay, thank you very much. Well, let me start by thanking you for the invitation. It's a pleasure to be here and give this remote seminar. Yeah, so today I will talk about some recent work about transport properties in QGP. So the idea is to use jets as a probe of the QGP and extract some information about the underlying dynamics of non-abelian plasmas. So of course here there are some keywords: wave turbulence, anomalous diffusion. So these are some of the emergent phenomena that I will discuss today. So this is a rough outline of my talk. So I'll first introduce the concept of jets in vacuum, and then jets, of course, in the QGP and why they are useful to study in the context of heavy ion collisions. Then I will dive into the topic, which is jet energy loss. How do jets dissipate their energy in the presence of hot QCD matter? And of course, we learned that this is going to be driven by turbulent energy cascade. Then I'll show how one can probe this and access this from data and study some of the observables that can tell us about this phenomenon. Of course, this is not going to be easy as it's a very complex problem, and experimentally it's very difficult to study. And last but not least, I will touch on the phenomenon of anomalous diffusion in the same context in QCD matter. So of course I'm showing here a picture that I stole from Wikipedia of the wake turbulence here in the wake of an airplane that's taking off here. And this is basically somehow an analogy with the topic I'm going to discuss today, which is that of a jet that goes through matter and that would perturb the surrounding medium and will dissipate its energy, transfer its energy. And the question, how is this energy going to be transferred, and what are the underlying mechanisms of such a phenomenon? So what are jets? So QCD jets are collimated sprays of particles observed in high energy collisions. So in E+ E- collisions, electron-proton, proton-proton, or even ion-ion collisions, which is basically the topic of today, which is heavy ion collisions. So here you can see here a display of a dijet event in proton-proton collisions from CMS collaboration. And so you see here back-to-back two narrow, somehow bunches of particles that corresponds to back-to-back jets. And you can see you have here leading jets. Jet 1 with PT of 585 GeV, and the wayside jet, which balances roughly the energy of the jet, because energy is conserved of the leading jet, and you get this dijet topology. So this configuration, this dijet configuration, is, as I will discuss, can be understood from first principles and from, in particular, perturbation theory. So jets have been studied for several decades since their discovery. In fact, you can really view jet as almost a direct evidence of the existence of partons, and in particular gluons. As you can see here in this 3-jet event, where you can see it here, this kind of Mercedes type event here, 3-jet event, where one of the jets, probably most likely let's say the fetter jet, would be a gluon here. And this is a remarkable evidence of the existence of the gluon through this kind of 3-jet topology. So this was predicted, they said, in late 70s and observed by the Petra collaboration in Yacine 79. So that was a rather successful test of QCD as a theory of strong interactions. So there's more to it. It's not only somehow a reflection of the partonic, let's say the leading partonic nature of the process. As you can see here, you have clearly here 3 partons in fine state. Jets are not partons. Jets are particles, hadrons that are absorbed in detectors. So how do we go from weakly coupled partons to confined partons in hadrons in the detectors, and in particular a large number of them, as I showed in the previous slide. So before going there, so as I said, jets are used as really tests nowadays, as tests of QCD, precision tests of QCD. As you can see in the left-hand side here, the coupling constants that has been extracted using different, of course, processes, but in particular inclusive jets here from the CMS collaboration. On the right panel, there's a display here of inclusive jets. And again, as I said, this is now reaching a stage of precision where high order calculations are coupled with resummation techniques to achieve a pretty good description of the data. And this is important not only for precision tests of QCD, but also for a beyond standard model search, and in particular for the Higgs search. So the Higgs discovery was made possible only thanks to these high precision calculations involving jets. This is simply because jets amount for a large portion of the background, the underlying background in the Higgs search. As you can see here, the signal, which is given in red here, is rather small and buried under a large background of jet events that need to be calculated and accounted for, and then subtracted to access the signal here, Higgs. As you can see, it's again picked around the Higgs mass here, which is 125 GeV, as of course observed. So this was important, and it's still important today for VSM search. But now what we want to do is we would use now jets as pretty precise tools to study the properties of the QGP. That's the goal that I'm setting here for this talk here. So as I said, jets are not just leading partons that are produced in elementary processes. We observe hadrons in the fine state. So what does QCD tell us about the dynamics that takes us from leading partons to hadrons? And in fact, although hadronization has to take place and confining forces have to be triggered to convert partons into hadrons at a given scale, which is lambda QCD, there is a wide room for weak coupling evolution, which is perturbative evolution, so to speak. And this is achieved, although the coupling constant is small, this is achieved through collinear branchings. So in any gauge theory, we have, although the coupling constant is might be small, the branch trialing process is enhanced by a collinear mass singularity and a soft singularity. And this collinear singularity is the reason why jets are collimated. And of course, because you have a large phase space due to this double logarithmic structure, you end up having large probability for multiple branchings to happen. And that's the reason why the final state is constituted of many particles. Of course, the conversion from partons to hadrons is less understood from first principles, but the phase that takes us from the 100 GeV to a TeV energy jet PT down to a few MeV or a few 100 MeVs here in the final state, this is understood from perturbation theory. So of course, there's more to it than simply iterating this process, this in a Markovian way. We need, of course, to account for interferences, quantum interferences, which to a first approximation simply amounts to ordering the cascading angle. And this is due to color coherence, which is just a reflection of the fact that soft gluons that are radiated at large angles must be suppressed simply because they don't resolve the inner structure of the jet. So they, instead of being radiated off multiple pronged object, they would be radiated off the total charge, color charge. The same phenomenon happening in QED. If you have a photon that splits into an electron-positron, the radiation pattern of this dipole is of course different depending on whether you look at the radiation, collinear radiation, which of course would be enhanced by the number of the final state charges, in this case 2 charges, and would be suppressed at large angles because the dipole would be won't be resolved and would look at simply a chargeless object, and so the large angles radiation would be suppressed. So this is why radiations, multiple successive radiation have to be ordered in angle. So that's the roughly speaking the structure of a jet. So, but we still need to define a jet. So this is what describes the dynamics of multiple branchings, but we still need to give ourselves an operational definition of a jet. So we need to give it a cone size. So we need to decide what is the size of the jets. So we can draw a cone around a certain axis and then say, well, that cone size would be r between 0.2 and 1, and collect all of the particles within that cone size, and that I would call it jet. So the number of jets in an event will change, of course, depending on the size of the jets that we're measuring. So this is really, so a jet is, well, it really depends on how we define them, there are other aspects to that definition related to the reconstruction algorithms. So depending on how we cluster particles in the final state from that we measure to kind of course, all of those algorithms, they have the same purpose, is to undo the cascading process here and somehow go back to the original pattern. But this procedure, of course, is not exact, as we, of course, that would mean that we have an exact knowledge of dynamics. We can only solve this problem, say, to certain accuracy in perturbation theory. So there will be some uncertainties related to that, and this is reflected in part in the different algorithms that are used to clustering jets here. So as I said, there is a large phase space for parton shower here, and this is the reason why the Platonic stage of jet evolution is so important in the study of jets in colliders. So you can see it here, the time scale between the production point here, where the hard event happens, and the hadronization, when hadronization occurs, is a very, somehow there's a wide window between these two time scales. So the hard process will happen at time scales which go like 1 over the transit momentum of the jet. As again, you can see it's pretty large, so the time is almost instantaneous, and then the time of hadronization happen at times that scale with PT instead of as compared to 1 over the PT for the initial time. So you see you have a large window with increasing PT. So this evolution is encoded in modern MC Monte Carlo event generators such as Pythia, Herwig, and Poig, and used in the study of jets in proton-proton collisions and all type of processes. All right, so what about jets in heavy ion collisions? So before we talk about jet, we probably need to introduce first the the colliding system, and how this differs from proton-proton collisions. So heavy ion collisions is the collision of two ultra-relativistic ions, as you can see here in the left-hand side here, are Lorentz contracted. After the collision, large number of particles are freed, in particular gluons, and start strongly interacting and eventually leading to the formation of the quark-gluon plasma. And this is a huge field of study trying to understand how thermalization or hydrodynamization may occur to reach the confinement phase transition, and how this somehow is sustained over a certain time, and whether the thermalization happens or not. So you can see on the right-hand side here that indeed from lattice calculations here, how the release of degrees of freedom going from hadrons to crossing here the confinement phase transition, going to the quark-gluon plasma. You see how the energy density somehow is this kind of jump that is a reflection of the release of larger degrees of freedom, simply because you have a more, the color degrees of freedom, of flavor degrees of freedom that leads to this kind of jump here. And as you can see, we expect the LHC quark-gluon plasma to sit around 600 temperatures, 600 MeV, RHIC here around 300 MeV, and so on and so forth. So the quark-gluon plasma is expected to form to high energy collisions at LHC and RHIC. So the question is how does thermalization happen? This is, as I said, is a rather active field of study involving plasma instabilities and turbulence and so on. And then eventually we reach hydrodynamical behavior. So there is somehow the other side of the coin, which is jets. So plasma is formed early on after the collision. It's made of relatively soft particles of about a GeV, a large number of them, and you can study them by studying bulk observables, such as just yield of particles, spectra, and so on, and flow harmonics, and extract some of the properties. You can also use hard probes being heavy quark, heavy flavor, or use high PT particles or jets that can be used as probes, high PT probes of the properties of the quark plasma. And this idea was put forward by Bjorken in '82, where he proposed to investigate the suppression of jets in hadron collisions as a signature of the formation of the quark-gluon plasma due to the energy loss. When jets propagate through the quark plasma, they would lose energy via elastic processes or inelastic processes, and they would lead which would lead to their suppression and thus signaling the existence of the quark-gluon plasma. So about 2 decades later, this phenomenon was observed at RHIC and then at the LHC. So as you can see here, we have a dijet event. In this sketch here, proton-proton collisions. You have 2-2-2 process here, a scattering process, producing 2 jets, back-to-back jets. Again, as I showed in the first slide, with this CMS dijet event display. And then here, this is a sketch of what this same event, the dijet event, that would form after the collision of 2 nucleons in heavy ion collisions. But of course, although while here the jet propagated vacuum, in heavy ion collisions, jet would propagate in a deconfined matter of quarks and gluons, and which would affect, of course, their yield and their properties. So on the right-hand side, the standard observable that is used to investigate this is kind of an emblematic observable, which is nuclear modification factor, which is defined as the yield of jets or high PT particles producing AA collisions divided by the yield in PP. Of course, there's a typo here, it should be PP, scaled by the number of binary collisions. So basically, if there were no final state interactions and heavy ion collisions, production of jets in heavy ion collisions were to be just an incoherent superposition of elementary nucleon collisions, proton-proton collisions, we would have this ratio equal to 1. But what we observe in here at RHIC for hadron spectra, high PT hadron spectra up to 20 GeV, we observe a suppression of about 0.2, which shows that basically there's some fine state interactions that is responsible for such a suppression. Here now jets at LHC, fully reconstructed jets were measured. And again, the same phenomenon is observed, that you have a strong suppression of jets all the way up to 1 TeV. So there's 1 TeV jets that are strongly suppressed when going through a plasma of particles of energies of about less than a GeV. So this is quite remarkable to see that high momentum particles go through a plasma of relatively soft particles and still get suppressed. So this is an order 1 effect, which requires a rather some sophisticated description to be able to account for such a huge description, a huge suppression. So in short, plane perturbation theory won't work, as plane perturbation theory is based on somehow calculating corrections, departures from vacuum. So we need to develop techniques that go beyond weak coupling techniques. So this is just to show you again displayed dijet event in heavy ion collisions. So you can see here in this, this is the 3D event display in eta, this is rapidity, and phi being the azimuthal angle of a dijet event, where one of the jets, this is the leading jet, 200 GeV jet, is not really balanced by the waveside jet, meaning that the waveside jet lost a lot more energy than the leading jet. So this is showing somehow the impact of fine state interactions and this imbalance of fine jet PT. So this is just to set the stage. So why do we study jets in heavy ion? I think I kind of touched on this and I motivated a little bit. And what do we learn about QCD by studying jets in heavy ion collisions? So first off, we want to probe properties of the quark-gluon plasma. So we want to send a jet as a test particle and learn, and by studying the probe, we want to learn about properties of the quark-gluon plasma. So not only that, we want also to learn about non-equilibrium dynamics, QCD dynamics, and the approach to thermalization. So by studying how jets are modified when traversing quark-gluon plasma and how energy is transported from the hard jet modes down to the temperature where energy is dissipated, we will learn about the dynamics of thermalization in non-abelian plasmas. So we also would like to learn about transport properties in QCD matter, and this would be the last item in this talk. What happens when particles go through quark-gluon plasma? What are the transport properties that will somehow be observed there? And then, of course, we can view this system as an open quantum system. So jet is produced. It's in a certain coherent state initially, but then when going through the plasma, this would lead to quantum decoherence and color randomization. And then the system is, of course, in contact with the reservoir, and that's understanding how this quantum system gets decohered is another interesting physics question. Okay, so here there is a first conceptual difficulty. So we want to be able to develop a first principle understanding of jet evolution and jet thermalization in a QGP. Of course, we can always assume that the QGP is a weakly coupled QGP, and we can understand it as we can use weak coupling techniques to describe the whole system, jets plus QGP, using coupling techniques. But in practice, and in general, there's a more general scenario where the plasma might be strongly coupled. And in fact, we should expect it to be strongly coupled owing to the running of the coupling. So the coupling constant is weak when at scales, hard scales of the jet modes. Then of course, when going down in scales, down to the temperature scale, the coupling constant increases, and then we should be able to understand how this transition happens. So the QGP is considered, from at least as was observed in the data, as a perfect liquid. That's probably the most perfect liquid ever observed, owing to the extracted viscosity to the entropy ratio here that you can see, which is very low, very close, in fact, to the Strock coupling limit that was derived by Policastro-Son and Starinets in 2001 using the n=4 Young-Mills. And this simply reflects the fact that the QGP might be strongly coupled at RHIC and LHC. So this begs the question, how do jet as weakly interacting partons lose energy to a strongly coupled QGP? So we can break the problem into two main blocks. So the first block is to say, well, in the spirit of effective field theory, so jets can be calculated from first principles using resummation techniques with a certain control over theory uncertainties, but completely based on weak coupling techniques, perturbation theory. This is calculable from first principles. Now, of course, there's a non-perturbative regime, which will rely on modeling such as hadronization and how energy is dissipated in the plasma if the plasma is strongly coupled, where we need to couple this with hydrokinetic theory. This would require some modeling. But the first block, we should be able to compute from first principles. And the way to connect these two blocks is to use transport coefficients. And in this case, the most important one would be the so-called Q hat, which is simply a measure of transverse momentum broadening here, which can be extracted from data or calculated from first principles or using lattice calculations. So this is basically how we would proceed. So we would use a theoretically controlled approach to compute jet observables coupled with transport coefficients that are non-perturbative, which need to be extracted from the data.
Yacine, just one question. So since you mentioned, so for the non-perturbative regime, for the medium, you can say that the temperature is the scale that determines the coupling. For the jet progression, obviously there's one scale which is PT, but I guess some virtuality is the scale you would think. Could be some square root P times the temperature or something else. So will you, maybe you'll come to it later, will you say a bit more on what scale determines the coupling there?
Right. So I will come to that. I'm not going to come to it precisely, but probably I should comment on this now. So there are many scales in the problem. So the first scale is the PT times R. So that's the virtuality, right? That's the virtuality. This is the let's say the hardest scale in the problem. It's about maybe, let's say, about 30 GeV, depending on the definition of the cone size, 30 GeV, just to give the flavor. So it's a pretty large scale. Then, of course, the jet will evolve from that scale and will degrade its virtuality, right? So the virtuality will go down. Medium physics, meaning the QGP physics, will be reflected before even you hit the temperature scale, right? So there's another medium-induced scale before, which is a global scale, before you hit the temperature. So the temperature is below, let's say GeV. That's a GeV. And the temperature scale would govern simply the dynamics of dissipation, the physics of particles that are of the order of the temperature that would collide, right? And then would somehow lead to detailed balance and thermalization. High energy particle that scatters off, say, a plasma particle, another scale would show up there. As you said, it would be more like square root of S. That would be more like square root of PT times the temperature. That's just square root of S of the colliding jet and plasma particle. And then there is another scale which would be related to momentum broadening. And this scale is simply the fact that when a jet goes through a plasma, it would receive multiple kicks. Each kick would be of the order, say, in fact, it's of the order of GT, G being the coupling constant times the temperature. That's the Debye mass. So it would receive kicks of the order of the Debye mass. But this would happen so frequently, right? It happens so frequently in diffusive manner. So it's like a diffusion, and it will accumulate over time. And this accumulation over time would lead to kind of the emergence of a new scale, which would increase with system size, right? The larger the system, that's a global scale. That scale is sitting between the hard scale, the virtuality, and the temperature scale. And numbers, to give numbers, this could be of the order of 5 GeV to 10 GeV. So I will come to that. And this would dictate the physics which will sit between the jet and the plasma. So there would be somehow a buffer region where a lot of non-equilibrium dynamics will happen, and then that's where the physics, the physics of how jets talk to the plasma occur.
Okay, thanks.
Okay, so the first item is turbulent energy loss. So how do jets lose energy? But before I go there, let me just say just a reminder of what turbulence is. So there are two. So when we think about turbulence, we think about classical turbulence. So which was understood formally by Kolmogorov and Obukhov in 1941. So how they understood turbulence back then is to look at the problem of injecting, so turbulence as an injection of energy at macroscopic scale, and this injection of energy just by somehow adopting this picture by Richardson, 22, where the injection of a larger scale would generate eddies at that scale, which then, because of their instability, would break into smaller and smaller eddies until they hit a scale, this viscosity, dissipation scale where viscosity would play a role, and then this would dissipate energy into thermal energy. But in between these two scales, between the energy injection and the viscosity and the dissipation scale, the dynamics of turbulence is local, in that it's not sensitive to the physics around the injection scale, nor the physics around the dissipation scale. So there will be some kind of scale invariance and self-similar evolution. And this self-similar evolution was the assumption that was used by Kolmogorov and Obukhov to derive their famous scaling here of k to the -3/5 for the energy spectrum of classical turbulence. So again, so this self-similar evolution and locality of interaction is the key ingredient here to kind of derive universal scaling laws for turbulence. But of course, here we're not dealing with turbulence, classical turbulence. We will be dealing with wave turbulence. And wave turbulence reflects similar features, but appears in, of course, a different context. It's context of nonlinear wave systems. There are a bunch of them. I'm just listing here a few of them. So you have atmospheric waves, waves on water, capillary waves, waves in plasmas, and you have also nonlinear Schrödinger equations in nonlinear optics, and also in Bose-Einstein condensate. So there are many, many problems where you have nonlinear wave systems where you can study wave turbulence. But the similarity with fluid turbulence lies in the inviscid transport of conserved quantities. So again, the fact that inviscid transport, meaning that in that window between, which is in the middle between the microscopic scale and the dissipation scale, in that window, energy is transported without accumulation. It just flows in a self-similar manner without accumulation. That's why we call it inviscid transport of conserved quantities. And this is what's going to happen also for jets going through the QGP. So this phenomenon, of course, is going to be a nonlinear phenomenon, and which would require resummation. So it's not going to be a plain perturbation calculation where we simply calculated order by order in the coupling constant. We'll have to resum to order a certain type of diagrams. But we need to recall recall here the elementary processes. So the first one being transverse momentum broadening. So I alluded to that after I answered the question, Rishi's question about the scale. So transverse momentum broadening, that's the first. So before even we start branching out, so it's just to have one particle going through the plasma, it will suffer elastic processes. So the elastic processes, which are multiple scatterings, will be responsible for transverse momentum broadening of the particle as it goes through the plasma. So the transverse will acquire certain transverse momentum, which is generated and accumulated via these multiple scatterings here. And this defines a transport coefficient Q hat, which is simply a measure of the variation over time of the transverse momentum squared of the particle. That's the elementary medium property here that we're going to use. But then, of course, multiple scattering could also trigger soft radiation. And this would lead to the phenomenon of Landau-Palmer-Schuch-Migdal effect, which I will describe in a moment. But then, of course, this leads to the radiation of soft gluons, whose spectrum is given by this formula, which is, of course, alpha S is due to the fact that you radiate a gluon. Of course, you have this factor here, which gives this 1/square root of omega suppression, which is the LPM suppression. These are the two elementary processes. This spectrum is generated again by multiple scattering. So again, this phenomenon is nonlinear. You have multiple scatterings that generate such a spectrum. And as I just said, that the QGP physics now is encoded through this this transport coefficient Q hat. So the rest of the calculation would be completely weak coupling, and all of the physics of the medium would be encoded in this transport coefficients. And going beyond this two leading or elementary processes, we will have, of course, to account for high order corrections that will lead to quantum interferences, RG evolution, and of course, turbulent parting cascade. So the leading order, you can calculate the skew hat to leading order in perturbation theory. So you can just consider a 2-2-2 process here. This is a G to the 4th process. This is the leading order, where I have here the leading jet parton that scatters with a plasma particle here, exchanging in the T channel transverse gluon here. And the spectrum is simply the Coulomb scattering here. It goes like 1/QT to the 4th. And that's the elastic cross section. And because we are computing the average transverse momentum squared, we have to weight it by the transverse momentum squared transferred here in this 2-2-2 process, and then integrate. That's how we can get a first calculation, leading order calculation of Q hat, which is proportional to the G to the 4th temperature cubed, which is the density of scattering centers, enhanced by this Coulomb logarithm. This is the leading order calculation, but as I mentioned before, this could very well be non-perturbative object if the plasma were not recoupled. And then we can of course use a non-perturbative definition of Q hat, which is akin to the gluon parton distribution function, is given by this operator definition, which involves field strength tensors with gauge links that make it gauge invariant. But for the purpose of this talk, we won't use this definition, and we will stick to the weak coupling description. So this defines Q hat. Now, the other elementary process, which is the inelastic processes, which are responsible for the multiplication of partons in the final state, or responsible for medium-induced cascade. This is the radiation process, which is induced by multiple scatterings, and this is an interesting process. This is a quantum mechanical process which leads to the so-called LPM suppression. So during this quantum mechanical formation time, so the gluon radiation takes a certain time to occur. This is given by the formation time. By the uncertainty principle, it's estimated to be omega over kT squared, kT being the transverse momentum of the gluon with respect to the jet energy, jet direction, omega being the frequency. And then this formation time, during this formation time, multiple scattering center can participate to the production of the gluon. And the accumulated transverse momentum can be calculated again using the transport coefficient Q hat by diffusion. It's just proportional to TF. And this is the way, by solving for TF, by just plugging this formula here in this formula for TF, formation time, we simply extract that the formation time has to scale like square root of omega over Q hat. And then we can also use this fact by simply the dimensional analysis to estimate how the spectrum behaves. So it's going to scale with the system size, because this radiation can happen anywhere along the medium. So it has to scale with the system size, L. Has to scale with the coupling constant because you have one gluon radiation. And of course, this leaves us with the formation time. So it's L over the formation time. That's how we get this 1 over square root omega scaling of the spectrum, which reflects the LPM suppression here. In the absence of LPM suppression, suppose we didn't have this coherent scatterings that happens here. We would simply multiply we would have the scaling of the spectrum with respect to the number of scattering centers. And then that's the Bethe-Heitler regime. We will simply have no suppression here, a flat spectrum that is proportional to the actual number of scattering centers, as opposed to an effective number of scattering centers that is suppressed by the formation time, the longer the formation time. Okay. Now, this radiation happens with equal probability along the medium. So it scales with the medium size. And this gives us a rate. So there's a rate here, the rate of radiation. And given this rate, we can write down a rate equation for multiple branchings, which would resum multiple splittings here that lead to the formation of a cascade here. Of course, each splitting here again is triggered by multiple scatterings, as you can see, and the formation time gives somehow the extent of such a process. But because the blob here is somehow has a certain extent, which is a formation time, which is much smaller than the branching rate, which is suppressed by an additional factor 1 over coupling constant. And again, assuming that the coupling constant is small, then the branching rate being larger than let's say the branching time here being larger than the time between two branches being larger than the time it takes to branch, then we can use kinetic theory to describe this process. It's given by a rate equation with a gain term and a loss term here. So what we measure here is the distribution, the energy distribution of final state partons here. And we would express it as a function of the momentum fraction of the final state particles. So the fraction of the energy fraction with respect to the original jet energy here. And then T is the time or system size. So what is the physics that, so now we have a rate equation, and by solving this equation, we will see how the dynamics of turbulence will show up. In fact, this equation will describe how energy goes from the large momentum particles down to the low momentum particles. So now we suppose we start with a single particle, which is sitting at 1. Basically, it's carrying all of the energy of the system, one particle. So after a certain time, this particle will start radiating and generating a spectrum. That's the 1 over square root x spectrum that I described, the LPM spectrum. And as the time goes by, we see that the spectrum starts increasing, but the exponent remains the same. It remains the same. And although the jet is disappearing here, this is due to the fact that the energy is flowing from right to left, the spectrums, the exponent of the spectrum remains the same. And this reflects, in fact, this is akin to the Kolmogorov-Zakharov spectrum. That's the equivalent, somehow the analog to the Kolmogorov-Zakharov spectrum for wave turbulence, with an exponent 1/2 here. And this reflects the fact that energy is flowing with constant rate throughout scales here, constant flux of energy. So there's no accumulation of energy throughout scales. It just goes locally from bin to bin until it reaches the temperature scale. Of course, here we don't have dissipation, so the energy would flow all the way to 0 from that equation that I showed before. But in practice, of course, it will at some point it will hit the temperature scale and dissipation will happen. And this is the wave turbulence inertial range here between the hard scale and the temperature scale. In between, you have this inverse energy cascade. So there, from these processes here, we can extract a few scales. So there's a stopping distance. There's a certain time for the jet to be completely to completely disappear. It's given by 1/alpha square root E over Q hat. There's a large angular scale. Basically, that's the scale where the cascade takes place, and so on and so forth. So these are characteristic scales that simply are generated by such processes. Okay, now we can. This was a sketch, a simple discussion, simplified discussion, which can be in fact solved analytically. This equation, given certain simplified assumptions, can be solved analytically. But we can do better than that and solve the full kinetic theory of the problem by taking kinetic equations, nonlinear kinetic equations, linearize them around the thermal distribution, and solve the problem. And then, of course, what happens? We could expect, different scenarios. One scenario would be that this inertial range won't be there. So the dynamics of dissipation would be non-local, and then we would see the appearance of or distortion of this Kolmogorov-Zakharov spectrum. But this is not what happens. So we still see 3 stages. So the first stage being the jet stage, the region. So this is the peak region where the jet sits. That's the leading particle, it's there. And the leading particle is losing energy via radiation to the bath. But how is this energy transported? Is it transported directly to the bath? Is it jumping in a non-local manner in momentum space so that energy goes directly to the bath? Or is there a more local in momentum space process? It's in fact local because it goes through this inertial range, which I described before. And the energy goes from the jet and it's transported through the turbulence, wave turbulent cascade, which is reflected via this Kolmogorov scaling here. Of course, we scale the distribution with square root of x so that the exponent simply shows up here as a flat distribution. So the power spectrum is flat here. And then, of course, when you reach the temperature scale, you have dissipation processes and detailed balance. And this is where the radiated gluons thermalize. And this bump here simply reflects the thermal distribution. So thermalization doesn't happen in a non-local way. It's really completely localized in momentum space. The jet does not talk directly with the plasma. It has to go through this inverse cascade. So again, interactions are local in momentum space. And the physics is completely non-perturbative. As I said, you have to resum a whole class of diagrams. And in order to see this feature, you really need to solve this nonlinear problem. And the key, one of the key lessons here is that the details of thermalization here do not matter in this phase, the turbulence and the jet phase. The only thing we need to know is the transport coefficient. If we know how to calculate the transport coefficient, we can precisely determine this, or precisely, well, at least given a certain accuracy, this phase, this inertial range, and the jet phase. Of course, when we hit the thermalization scale, the thermal scale, then the dynamics is nonlinear, and we we need more than simply the transport coefficient. But in this regime of turbulence and the regime of the jet, it's sufficient to know the transport coefficient to be able to describe that physics. And as I said here, the equation that I introduced here doesn't know about thermalization, and yet it provides a pretty good description of the physics in these two phases. Okay, so I see that I'm running out of time. How much time do I have left? I
think we have maybe 5 more minutes.
Okay, so I would probably skip this part and just go to the anomalous diffusion part. So maybe still, let me just mention here that we can, after answering the question of how a single parton loses energy, we still need to answer the question how a multiple partonic system, which is a jet, so a jet is a multiple partonic system, lose energy. And of course, due to quantum interferences, this is not going to be simply reflected by the incoherent sum of partons that lose energy. So we'll have to solve a problem, nonlinear problem, where depending on how the plasma resolves the jet or not, it would trigger a radiation of multiple partons or the total charge. And this would affect the observables, in particular the jet spectrum. And this coherence physics, let me just skip this, can be described by a nonlinear evolution equation for the quenching weights, which are simply proxies for the nuclear modification factor. It's a measure of how much energy is lost by a single parton. But if you have many of them and they interfere with each other, you need to resum all of the multiple branchings here through this type of evolution equations, and can be tested against the data. So the nuclear modification factor here, measured by the CMS, the Atlas collaboration for different centralities, we would just somehow try to, it was an attempt to see whether this description, rough description, but yet quite in agreement with the data, as a first try to see whether this physics can be observed or not in the data. And of course, this would provide a way of constraining the various modeling that can go into the description of the jet by varying supposedly, if you can vary if we relax certain approximations, whether this would be seen in data or not. So this is really constraining, as we can see here, by the rather good description of the data here. Varying parameters would lead to rather significant deviations. Okay, so this is the last item since I don't have much time, but I think this is worth mentioning here, which is the anomalous diffusion. So the question that I would like to ask here is, what are the effects of quantum corrections on transverse momentum broadening? So the diffusion in momentum space can be described to leading order, as I said, and leads to the standard diffusion and standard linear scaling or square root scaling of transverse momentum with time. And the question is, and this is a reflection of locality in this diffusion process. Now, quantum corrections are non-local. The question is how these quantum corrections affect the microscopic measurement of transverse momentum broadening. So this is just to recall what I just said. You can describe transverse momentum broadening, which is just as a diffusion in transverse momentum space. So the particle would just diffuse in transverse momentum space. Transverse momentum with respect, of course, to the direction of the jet. And as a standard diffusion or normal diffusion process, the transverse momentum square root scale like the time. This is the classical picture, so to speak. Now, if we add to that quantum corrections, so quantum correction meaning adding gluon loops here and see whether they lead to large contributions. So we know we have examples where quantum corrections are very important. In fact, they are critical in our understanding of the proton structure. So you can go from the naive parton model where you see the proton is just a collection of 3 valence quarks, but in fact, there's more to it. Quantum corrections to lead to the running of the coupling, to the introduction of gluons as degrees of freedoms, to confinement, and so on and so forth. So really, quantum corrections, our understanding of quantum corrections and how the RG evolution tells us about the nature of QCD dynamics is really essential to understand the physics that we are studying here. And in fact, this leads to qualitative differences. So at tree level, no quantum corrections. We have the standard Gaussian distribution. So as I said, you have diffusion. So diffusion is Gaussian. You get a Gaussian distribution around the typical transverse momentum, which is Q hat times the system size. Q hat times the system size, that's basically what you expect. That's the typical transverse momentum. It scales like the length of the medium. Then at large transverse momentum, you get the power law, which is just the Coulomb tail, 1 over kT to the 4th. That's the tree level distribution. Then Q hat to leading order, that we'll call it now leading order because I will go on and calculate next to leading order corrections to Q hat. It's just some, of course, prefactor here, which is density of scattering centers times the Coulomb logarithm here. Here, this is a transverse momentum distribution, which is most easily described in Fourier space, coordinate space, where we can exponentiate multiple scatterings. So the exponential of multiple scatterings can be exponentiated by this Glauber-Müller type of formula. So you see the Gaussian nature here of the distribution that leads to this, again, Gaussian in Fourier space. So this was calculated for length of the medium 6 Fermi, which is realistic, and Q hat naught 0.5 GeV squared per Fermi. And you get typically a typical scale here of the order of basically between 1 and 10 GeV. Now, recently, a few years ago, it was observed that the next to leading order correction leads to large logarithmic enhancement. As you can see, you have an unbiased correction here, which is simply the addition of a gluon loop. But then you get a large, potentially large double logarithmic enhancement of the system size. So it's the log of the system size, and tau 0 being typically the mean free path. So you have the mean free path, that's the microscopic scale, and then the system size, that's the macroscopic scale. So this means that high order corrections need to be resound and might lead to modification of the of this classical picture. So these double logs can be resummed to all orders using a renormalization group equation that allows us to resum to all orders those double logs that you can see here. So the double logs are simply collinear and soft logs, as I introduced in the beginning of this talk. So Q hat, the evolution of Q hat with respect to the system size is given by this double log equation. And the important feature of this equation is that although it's linear, it looks linear, it's not, because it knows about the existence of multiple scatterings. So typically this gluon, the double log lives in a region where only one scattering is responsible for this non-local gluon radiation. But this non-local gluon radiation may encounter other scattering centers. And in the regime where this gluon can rescatter multiple times, this is the regime where you lose a log. So typically the double log really is restricted to a regime where only single scattering happens. But you need to constrain that phase space. And this phase space is constrained by this saturation line. So in this plot here, KT versus the system size here, in this triangle here, inside the triangle leaves only single scattering, where gluons can be triggered only by single scattering. Why is it important? It's important because it means that the interaction can be seen as local. It doesn't know about the system size. But in fact, it knows through this saturation line here, which is a boundary that tells us that beyond that boundary, multiple scatterings can deplete the radiation rate. And this is reminiscent of saturation physics and the color glass condensate. So this is the physical picture. So you have local, at leading order, tree level, you have local interactions. Take basically the correlation length is of the order of the inverse the bimass, or which is the local scale, which is microscopic scale. So the particle will scatter and then takes a certain time before it scatters again, and so on and so forth. This leads to the standard diffusion. Now, high order corrections lead to non-local, of course, interactions. So this is a sketch of what happens. Of course, you could have one gluon interaction here, but you could also have an interaction via multiple gluon exchanges here, or radiation, which take a certain time to happen, and those gluons could overlap. And this overlapping gluons are suppressed, and the only piece, which is the disconnected piece, can exponentiate, given that, of course, the phase space constraint that I described before. Still, these interactions are not local, and because they are not local, they would modify the scaling of the diffusive process. And this leads to a super diffusive process. So one of the, and this is somehow, this super diffusion process is also observed in the so-called Levy flights. So Levy flights, as opposed to Brownian motion, which is completely localized here. So you could have a process where a particle would diffuse locally and just stays around a certain area, and the size, of course, of the somehow the extent of the area that this particle would cover scales with the square root of time. But the Levy flight process could, of course, explore wider areas simply by, of course, coupling with a standard diffusion. You could diffuse locally, and from time to time, with a probability that is not negligible, it could jump, a particle could jump from an area or region to another, and will explore arbitrarily large distances. This leads to this super diffusive process leads to the non-locality of the diffusion here. And one of the reflection of this process is the scaling here, which is again a reflection of the self-similarity of the process, because there is no scale that dictates the size of the jumps. You get the scaling, and if you plot the distribution for different system sizes with respect to, instead of plotting it as a function of KT, but KT divided by the saturation scale, which is the typical transverse scale of the problem, then you get all of the curves going on top of each other, exhibiting that geometric scaling feature, which is again a reflection of self-similar behavior. So to solve this problem analytically, we can draw an analogy with traveling waves, which are also some nonlinear systems where some exact solutions are known, in particular the Fisher-Kolmogorov-Petrovsky-Pesnukhinov equations, which are used for population growth and wave propagation. These are nonlinear equations that can be solved exactly and lead to similar geometric scaling solutions. They were also used in a QCD context in the problem of saturation physics, and in an attempt to solve the Balitsky-Kovchikov evolution equations that describe the evolution of gluon distribution at high energy. So these are different problems, physics problems, but in fact they share very similar features related to nonlinearity, stochasticity, and so on and so forth. And we use the same techniques. Without going too much details, you can extract asymptotic results, which can be calculated. These are universal distributions, which are not sensitive to the initial conditions. So these are universal results, which display the scaling behavior. These are the scaling feature here, in blue. This is asymptotic limit, x being the scaling variable. You can also compute subasymptotic corrections. You can go even to higher orders. And then we compare to the exact numerical result. And by comparing to the exact, that the blue compared to the orange, we get a pretty good description, even for system sizes that are not very, very large. So the asymptotic result without the subasymptotic, pre-asymptotic corrections, this is the dashed line. So we are kind of, you see how the pre-asymptotic terms are important to get from the asymptotic to the exact numerical result. And also, just I think it's worth comparing with the tree level. So you see here that the tree level, which is given by the dotted dashed, it's this Gaussian distribution, and then the 1/k to the fourth is rather different. So it's more peaked, while the final scaling distribution that resums quantum corrections is fatter distribution and displays this kind of heavy tail here, which is akin to Levy flights. So this is very important. So we have a wider distribution and a heavier tail, which is reflecting again this Levy dynamics. So just to wrap up here, this is again the median KT, which is just the typical transverse momentum squared, and then compared to the normal diffusion. So this is transverse momentum. This is the median, but you can look at it as just the typical transverse momentum as a function of the medium length. And the dotted dashed here is the tree level. Tree level scales like roughly the time or system size. There's an additional log, which is due to the Coulomb log, but typically this is normal diffusion. But the quantum corrections lead to the resummed quantum correction lead to this anomalous scaling. So there is of course a scaling here exponent c, which is larger than 1. As you can see, it's 1 + 2 squared of alpha s. So this is a super diffusive process. Basically, you diffuse much faster than normal diffusion. And of course, we have also calculated subasymptotic corrections here. And you see the comparison between the analytic result and the numeric result, which is pretty good. So this is again the fat tail I just mentioned. You see it here again. So comparing the large transverse momentum region, comparing the leading order 1/kT to the fourth to the actual resummed result. You have a fatter distribution 1/kT to the power -4 plus square root alpha s. And again, this is a reflection of this asymptotic behavior and the geometric scaling feature here. So this brings me to my summary. And yeah, sorry for going over time. So jets provide a multidimensional and multi-scale probe of the QGP. So we can use jets really to probe the dynamics, non-equilibrium dynamics of QCD. So we can use it, of course, as a theorist to kind of learn about the dynamics of QCD, but also we can confront these theories and our understanding from a theoretical point of view to the data and try to extract this and from observables. Of course, this is not so easy, but this is a first step. Try to understand, of course, the basic physics. So there are a couple of emergent phenomena that I touched on today, in particular the turbulent transport of energy from jets to the QGP. Typically, the bottom line is that the energy is not injected directly from the jet to the plasma, but it has to go through many order of magnitudes in transverse momentum space through an inviscid turbulent cascade, inverse cascade. Then, of course, I didn't have time to really discuss color decoherence, but I discussed the anomalous diffusion, which is a reflection of quantum corrections to the diffusion in transverse momentum space, and the effect is rather remarkable as it's a qualitative effect. So you go from normal diffusion to anomalous diffusion, super diffusive behavior. So this super diffusive behavior also comes with some, of course, perks here, which is, for instance, geometric scaling. So the distribution can be studied experimentally and try to look for such a geometric scaling. Look also for the heavy tail, look for the exponent, and see whether it's there from the experiment. So this sets somehow a basis for further exploration of those emergent phenomena and exploring them from a theoretical point of view by going after high precision calculations and high order calculations. And of course, from a phenomenological point of view, try to really investigate them in experiment RHIC and LHC via a collection of observables that are designed or suited for highlighting this phenomenon. That's Just giving here non-exhaustive list like dye-jet correlation, jet substructure, dye-jet asymmetry, and so on and so forth. And thank you for your attention.
Thanks, Yacine.